So, this is just to give you an overall idea of how to implement design of experiment, and what is the basic idea of the design of experiments is also is here. Okay. This is a general overview for DOE. You want to learn and improve, that is the basic idea in any design process. There are multiple ways in which you can do. One is by observing significant events, one is you have previous knowledge, you have legacy, and the third one is simulation of events. Okay. In order to do 1 and 2, you have to interfere into the process, okay, whereas 3 is good because it is a computer simulation, you can simulate the event. But the moment you want to simulate the event, you will have to replicate these guys, that becomes important. You understand what I am saying? Let us say that you are trying to model rainfall and you have last 50 years information, then you build a model. Your model will never get the 2015 rainfall situation. It will never get it, because your model is based on the last 50 years in which we never saw that kind of a rain or tornado or whatever your wind speeds. If you do, your model will never capture the Varda. So, what you have to do is you will have to try to simulate this significant event. You will say it will happen 1 in 100 years, but your model should have that kind of a nonlinearity. You have to do that. If you can do that, then you can do simulation of events. Okay. What is the idea? This is similar to finite element. Okay. There is a truth is here. Okay. The truth part is here. It is kind of a nonlinear stuff. I could still do a nonlinear approximation, or I could do a linear approximation. It does not matter. The truth is not known. This is the actual stuff, but it is not known. What happens to a occupant under a specific crash condition? You will never know what the truth is. You cannot do an experiment with a real person inside. You will do it with the dummy and you hope that the dummy is correlated to the human being, that is all. Okay. So, you do not have this information, but we hope this is closer to that and then we try to do this. This is not such a good experiment. You will have to correlate the few points that you have and then you will have to adjust this guy to this guy. So, end of the day, this is what we spoke about. The two things that experiment that DOE can let you do is can give you some statistics of this and it can let you construct this f function. The general process, I did not discuss this explicitly. For instance, you have something called key control parameters. You have key noise parameters. You cannot do anything about this noise. You know that these are noise. You have to live with the noise. The roads are bad in India. You are a car manufacturer. The roads are not, let us not use the word bad, it is not that good in India. You say, okay, let us wait until the roads get better, then we launch our cars. Today you name the car that is there in the Indian roads. You name a car, that car is there in the Indian roads. Anything from your Lamborghini to your Rolls Royce Ghost to anything that you name, it is there. Ferrari, everything is there in Indian roads. Need not be necessarily in Madras, it is there somewhere. Okay. So, these are all sometimes they are all like fast moving cars, sports types of cars, anything. They are not designed for Indian roads. Okay. So, they say no, let us not launch this because the Indian roads are not good. And someone buys it at few crores and let us say that it fails on day 4 because the roads were not good. That is also not acceptable. Right. So, this is noise parameter which is not under my control. I know these are the noise parameters, but I do not have it under control. The way you guys are attentive to me is a noise parameter. All of you are not the same. The way you sit, the way you nod, the way you put your head down, the way you do this, it is all noise parameters to me. But I cannot I will not say that okay, let all of them be fresh and then I will start. That can never happen. So, what I do is I try to minimize my reaction to what you are doing. I make myself insensitive to your noise. That is what is robust design. So, the key control parameters I have, key noise parameters I have, and this x is your input. Okay, this x is your input, which is your independent variables, and the y is the dependent variable on your x. So, essentially you are interested in this f, finding this f that relates your y and x, that is all. and our whole point is also to simulate these guys, to understand the effect of these guys and to simulate these guys. What is the DOE workflow? It starts in a design perspective. Okay. So, first you will have to identify the problem clearly. You will have to study the objectives of your, you will have to lock your objectives. Sometimes, as you pointed out in the kiln example, in the tile example, the problem was the tile output, okay, the variation in the tile dimensions. But you should know what is it that you are looking at to address. You cannot go and address the non-uniform temperature, you will have a problem. You should know that I will identify the combination of my inputs that go in. Okay. So, that becomes important, you will have to state your objectives. Then you will have to correspondingly identify your variables that will contribute to that objective, which essentially will address the problem. You identify the responses, it is not always one, it could be multiple responses. From this you select a few, you do not carry all of them, you select a few. Then within that you define your factor levels 3, 4, 2, whatever it is. Then you do your design of experiment, which could be orthogonal array for us. Run those experiments in some randomization, blocked, complete, whatever, simple, and then you study your hypothesis. So, what we have discussed so far is this DOE we have done. Running the experiment, we imagine that you will be able to do some kind, at some combination you will be able to do, right. Then you will have to study the hypothesis. What does this mean? It could be your quality based study, it could be your robustness based study. Okay. These are all out of scope practically for us, how to choose the vital few from the trivial many and all that. Usually you do something called PCA, principal component analysis, there is something called factor analysis, you can do that, and sensitivity study you can do to identify which factor or the response is sensitive to which factor the most, then you select only those guys. Okay. What are the objectives or goals of DOE? One, please understand this is slightly different from what I told you earlier. What DOE lets you do is different from what could be the goals of DOE. So, this is an interesting stuff. So, if you look at it, it can let you do comparative experiments A versus B, which is better, is A better than B, without getting into the physics. There are two ways of looking at it, right. You build a model, you understand the physics, and then you tell whether A is better than B. But oftentimes you cannot do that. The furnace example, you cannot touch the example. I do not know the physics, I only have a product with me. So, what I do, I get 2-3 products and then I test, and then I will say this product is better than that product. So, DOE lets you do that. For instance, you get 2 different bikes, motorbikes, and then you are a reviewer in XBHP forum. You just drive it in one setup and then you say this bike is better than that bike. You cannot post a review like that. You will have to test it in different conditions. Okay. You will have to ride it in a muddy road, you will have to take it up a hill, okay, and then you will have to check on different parameters, how fast it went from 0 to 100 kilometers per hour, okay, what is the fuel efficiency, on different attributes, on different levels you will have to try. Okay. You will have to try the mileage, driving it early in the morning, at 1 o'clock in the afternoon, in the night, okay, and then you subject it for continuous riding for like 3 days, and then you check what was the mileage. You continuously ride this guy, okay, as much as full throttle, you abuse this vehicle for like 3 days, and then you check what was the mileage. Similarly, you abuse the vehicle for 3 days and then you do it. Then only you can say that this vehicle in an overall sense was better than this vehicle, or this vehicle was specifically good in these areas and this vehicle was specifically good in these areas. So, you cannot just do one condition and say all the different attributes that a combination that I told you is what your design of experiment is. So, you will have to design your experiment in such a way that it will get abused, it will get in a nice combination, it will go in a hill, it will go in a flat terrain, it will go into a valley, whatever it is. So, all this are you are trying to simulate the different combinations. Okay. So, then I will be able to tell you a comparative study of A versus B, that is one thing. Then you can also conduct an DOE to identify the vital few from the many factors. Okay. So, that will tell you which factor is important. Column wise when it says this factor is more affects more the response, then you will choose only those factors, but this will be a preliminary design of experiment. Then you can do something called the response surface modeling. It is nothing but getting the f using some regression models. You can identify f. See, if I give you a bunch of x and y, we have been talking about this for a while. I will give you an idea on what this is. I did some experiment. X is a dimension, y is a response. For different dimensions, I have data like this. I have this data. I gave this data to you, and then I said, hey, I forgot, can you go and find out for a dimension of 8 unit, what is the response value? You have this data with you, and then I told you, can you go and find out for a data value, new data value of 8, what is the response value? What will you do? One way would be to go and conduct an experiment at this x and find the y, but is that the wise way to do it? No, the wise way is just now what this guy told. He says, I will look at the data and it kind of exhibits a trend. So, can I do this? If I do this, then probably I can just say that this is my y, and I will be able to, the moment I construct this, I will be able to tell this for any x that you ask me, any number of x's, which means I can get rid of the experiment that you are trying to do. This is what is the f of x that we are talking about. What is our f of x in this case? If it is the red line is represented with what equation? So, this equation is you will know y, you will know x, that is what I put as dots here, correct? It is just, this is x1 y1, this is xn yn, this was x4 y4. So, there is an x, there is a y. So, like that I had 7 x's and y's, and that is what I have plotted. The second point is, how did you get this graph? You go to Excel, you put this and then you say trend line, then it will give you this. But practically how do you get it?
We try and take a line such that the distance, such that the distance, least square distance, we try and minimize the distance.
Yeah, one second. The question is, what he told us, right? The question is, I can fit infinite number of lines through these points. Which one will you select? And please understand, none of these lines could pass through all the points. That is not possible when there is variability in your data. If I drew the lines like this, then you can say, okay, I will draw a line that passes through all the points, but I did not draw like that, I drew like this. So, what will be your criteria to draw this line?
Taking the mean.
Mean? Mean is here, this is the mean.
Mean is standard deviation.
If this is the y, this is the mean for you.
So like, with all the data points we can calculate the mean and plot the standard deviation.
No boss, this is the mean,
Yes, sir.
this is the mean. What do you do after that?
So standard deviation we could reduce and try to
Standard deviation of what?
all the points.
Okay, you compute the standard deviation of all the points, then what do you do?
So then we can reduce the which line has the minimum standard of deviation.
Standard of deviation of what? You are coming to the point, but you are not, at least you are not expressing, if I am not. Standard deviation of what? Okay, so here is the point. You draw this curve. For this particular point, the actual value is this red dot, but what the line gives you is this. So, what is there? There is a error. Similarly, there is an error for this guy, there is an error for this guy, there is an error for this guy, there is an error. Actually, the line should come here, so there is an error for this guy. All the green vertical lines are the errors between the actual dots and the line that you have fitted. Whichever line you take from this will have this error, because none of the lines is going to pass through all the points. So, now what could be a logical criteria for you? Logical criteria, sorry,
Least error.
you want to choose a least error, but then you have more errors here, you do not have one error. So, what do? Average is one thing, but you do an RMS. So, you should be careful what statistics to use when, right. So, you will use an RMS because you want to get one metric out of multiple values. So, RMS is what you will square your errors, you will take a mean of it, you will take a square root of it, that is your root mean square. Why you will square is because you will have errors on both direction. So, they should not go out to be 0, that is all. Okay. So, what you will do is this, you will change your M and C. M is the slope and C is the intercept. So, they will control, if I am going to change the C for the same slope, what will happen? This curve will become this curve. Okay. For the same C, if I am going to change the slope, it will become like this. So, this M and C is your design variable. So, you are going to change them while you record your errors. So, what is it practically? There is an M, there is a C and there is an RMS error. So, for different M and C, I will have different RMS errors. Imagine you are not going to do that, you will use an optimization algorithm to do that. If you do all this, what you will do is you will go and find something where the RMS error was less, and then you will choose the corresponding M and C's, M optimal and C optimal. This is how this is called regression, because you are trying to regress the values or the residuals, you are trying to find the M and C, and this can be generalized. Okay. You can go and generalize this to y equals beta naught plus beta 1 x plus beta 2 x squared. You can just write it simply like this, beta I x I, sorry, no, not x I, sorry, x raised to I. Okay. So, if you say 0, I running from 0 to n. So, beta 0 x 0 is 1, then beta 1 x raised to 1, beta 2 x raised to 2, and you can also build it into an ij provided you have x 1 x 2. So, if you have x 1 x 2, you will write it as beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta 3 x 1 x 2 plus beta 4 x 1 squared plus beta 5 x 2 squared. So, you can keep on doing this, it is all fun, okay, but this is not the scope of this course. So, the idea is you can fit a response surface, this is called a line fitting, but the moment you have 2 dimensions, it is not a line anymore, it is going to be a surface. Okay. So, this is important, you need to have a function that relates your, because this is the function that we are talking about, this is the function f that we are talking about. This is how you get y, x, and then you find the relationship. Okay. So, this is the response surface that we are talking about. So, using that you can find a target design, you will be able to minimize the variance, you can find the minima or maxima of the response, you can do robust design, you can do reliable design, you can do optimization, you can do design space exploration. There are multiple things that you can do with that, provided you create a surface like this. Okay. The other things is, how do I identify these variables and responses? These are stuff that you might have come across in a what you call functional conceptual design, the fishbone diagram, what leads to what, otherwise it is not a big deal. See, what you do is this is called working condition, you are not able to read this, but do not worry, I will just tell you what these things are. So, this is the main one, and then these are the bones that lead. For instance, this one is called working condition raw materials management. I will tell you what the flow of the working condition, it says noise, illumination, humidity, temperature, these are the factors that, and then raw material it says moisture contents, delivery time, shell life, strength, storage condition, all these affects. Okay. And then you can also have multiple things from here feeding to each of those bones, storage condition, temperature, humidity influences that. Okay. So, you build all these things and then all of this leads to a poor quality product. So, from this you identify which is the most important one, they are all close to the right side. Okay. So, that is and then you can now have a brainstorming, you can have customer inputs, process map, you can do failure modes, effect analysis. This is one of the key things that people try to do, okay, to identify the fuses. So, that was just to give you an idea of the general design of experiments. Okay. Now, this is just one more stuff I wanted to say. There is some limitations with respect to the orthogonal array. Okay. One more from the sampling perspective itself. Okay. What is it? You see this picture here, this is an orthogonal array representation. So, x1 is in this axis, x2 is in this axis and x3 is in this axis. Now, how many points along x3? 1, 2, 3, 4, 5, 1, 2, 3, 4. So, if you take this particular plane, the plane that I have drawn, it is x2 and x3. Imagine that you are standing on this side and you are just looking at this direction. Okay. Your depth information is lost. If you are projecting x2 and x3, your depth information is lost. You are only getting the 20 point information, but how many simulations have I done? I have done 60 simulations, because 20 times 20, 20, not 20 times, 20, 20, 20, 3 times 20 is 60 simulations you are doing. At 60 different points you have done the simulation, but out of that, if I take a projection of x2 and x3, I am getting only 20. The idea, the picture in the right is to drive that idea. Okay. If you are seeing through this guy here, this is like a orthogonal array condition. Okay. So, what is happening now? Imagine that each of these guys are points. Okay. So, similarly, there is a point, I keep one point, but actually there is 20 points behind that point, correct, right. So, when I am seeing from here, how many people I am able to see? I am able to see only one guy. So, in a projection, I am able to see only one of that guy. Of course, if I go to the other direction, I can see, but please remember, I will be able to see those 20 people, but I will not be able to see the guy behind him. I will not able to see this guy, I will only see this guy. So, still I am losing that information from that projection. So, what is happening is, though you run the simulations at the 60 samples, the information that you extract in a projection sense is only 20. This is one problem with orthogonal array. How can you address this problem? Very simple. If I want to see more people in this row, in this particular row, if I want to see more people, what can I do? It is simple, man. For a very long time, the guy at the back was hidden behind this guy, knowingly or unknowingly. Okay? I am not able to see. He is sitting. Now, imagine that 20 people are sitting in this, and I am not in a podium, I am facing you like this. I will not be able to see the other people, but I need to see the audience reaction to teach. So, if I want to do that, what should I ask you to do? So, you move, but then you are going to block the other guy, next guy. So, what will you do? Stand up, huh? Yeah, so let us say that I put a roof on top of you, you cannot really stand up. That is what is your design bound, you cannot go beyond your bound, right. So, there is a practically you cannot stand up, yeah. Meaning we are talking only about this window projection. So, you cannot get up, that is the window projection that I am talking about. What can you do? Sorry? No, that is height wise. Think the same thing in a projection sense, correct. That is the reason why CLT and all that you have that kind of a stuff, sorry. So, you will have to move and see, okay. When you go to your what you call theaters, okay. So, there are two types of mix. One is along this axis also there is a mix, you don't sit in the same line, okay. This line is also like this, and you don't sit one behind the other. With this elevation also, the one seat is between the other two seats, there is a small overlap, right. So, now if that guy has to see me also, he has to just push his head a little bit. So, if I want to extract more information, what I need to do here? I need to push this point a little bit, because right now this guy is just behind him. So, if I want a little bit of information, I will just push this guy a little bit. Similarly, imagine that you perturb the 60 points or the 40 points a little bit. Then if you take a projection, you might not get 60 information, you might get at least 55 to 58 information, correct. So, this movement you need not do it randomly, okay. There is statistics to do that for you, and there is some quantities that you might want to preserve and do it, okay. Those are called space filling techniques, and one of the widely used technique is called a Latin hypercube sampling, okay. So, the idea in that is it is stratified in all the dimensions, not in a particular dimension that you talk about, and the projection onto the variable axis is also uniform. So, a very simple example of a Latin hypercube, this is only to give you the scope, we will not get into the details and all that, right. So, there is a min-max algorithm, which means it minimizes the maximum distance between any 2 points, so that you get total exploration of the design space, okay. The basic idea between LHS in a very layman term is, let us say that you have about 10 points that you can do. What I do is I divide the design space into a 10 by 10 grid. Then what I do in a random sense, I allot one point to a particular column, in this case it was column 1. Then I immediately lock that column and that row. I will not put any other point in that row and in that column. Then I put the second column in this row in a random sense, then immediately I lock that row and that column. So, when I keep doing like this, okay, this is exploring, because there is a 10 by 10 stuff, and for sure you will get 1.1 row in one column, okay. So, this is all you can do with the 10 sample stuff. So, instead if you used 100 samples in this case, then imagine that it will be like very small in this case, right. We are almost close to. So, if you have a equidistant stuff, and what we are saying is I am going to take points here, right. So, if I had an x and y, for whatever x's I did right now, my y values will be 0, provided this was 0, but that is not my curve. If you are going to fit this guy and this guy, what will you get? You will fit like this, that is not my curve. So, instead if I am just pushing this guy a little bit this side, here, 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 here and here, something like that, then again I might not get this curve, but I will at least get something like this, okay. So, there is one limitation with the periodic sampling. Orthogonal array is kind of a periodic sampling, okay, but there are a lot of advantages of orthogonal array that is evident from the profits and the huge success in the manufacturing industry. It is based on a very strong scientific principle, and manufacturing industry has heavily benefited out of Taguchi and Six Sigma principles, okay. So, this is the idea behind the space filling techniques, okay. So, let us not, it is the max min distance, maximize the minimum data. Did I write it as min max? It is a max min algorithm, sorry, maximize the minimum distance between any 2 points.